Okay, so I will be working on chapter 18, hopefully part two, and yeah, this is part two for sure, but hopefully this is the last part. If not, I will have a part three. Anyway, let me quickly recap where we left off before. We were talking about the second law of thermodynamics, and this is where we left off last week. And in the second law of thermodynamics, what was being revealed is another condition, a second condition that has to be met in order for a reaction, any kind of reaction or process, to be spontaneous. So when we left off last week, I was describing this second condition. Okay, so we're told here, according to the second law, that the second law of thermodynamics says that the total entropy change of the universe. Now, in chemistry, we're not used to looking at things from the universal level, but for the sake of this chapter, we are looking at things at that macro, the huge macro level, which is once again when processes are spontaneous. They're spontaneous because, and this is a justification, because this prerequisite, this condition, this threshold has been met. Okay, so if you want a process to be spontaneous, you want to make sure the total entropy change for the universe has to be positive. Okay, and we're told here this is a requirement that's mandatory, it has to be met for a process to be spontaneous. So we are acting like inspectors, inspectors of spontaneity, and we have a little visual or mental clipboard, and we're trying to check off requirements. Have the requirements been met for a reaction to be spontaneous? So what are these requirements? I kind of segued and listed them right here based on what we've covered so far. These are the requirements or the criteria that have to be met for a reaction to be spontaneous or for a process to be spontaneous. It doesn't have to be a chemical reaction, it can be a physical transformation. So, the first criteria, imagine our clipboard, right? The first criteria is the following. If you're given delta H and delta S values for that reaction or that process, you want to look at those two values together. So they're like a combo, right? You want to look at these together, not apart. And then you want to judge together. Do these provide you with the signs that communicate to you that this process is spontaneous? So we are looking at these two numbers, not the actual number, but the magnitude, right? Wait, the magnitude is a number. Sorry, the sign. Okay. So delta H has to be negative while delta S has to be positive. So when you have these two together like that, delta H being negative would just mean saying that, another way of saying the reaction is exothermic. Delta S being positive, what we're saying is the reaction has to end up having a higher entropy. If the reaction is more random or has a higher entropy, now the reaction also means the process. When you have these two happening together, then we can confidently prove or conclude the process is spontaneous. Okay. The other criteria is the one we just read. Maybe these processes aren't don't have these signs, right? The process we're looking at may not have the following signs. What else can we look at? Well, the other thing we can look at if we don't have a delta H or delta S value is we can look at the delta S of the universe. Look at the entropy change of the universe, which is what this is, entropy change, and then judge by the sign. Is the entropy change of the universe, is it positive? Okay. So just looking at the entropy change, though, you don't have to look at that number in combination with another number. You can look at this number by itself. Unlike this first scenario here where you have to look at the combo, with delta S, you can look at this number by itself. Delta S of the universe has to be positive by itself, according to the second law of thermodynamics. If delta S of the universe is positive, then you can judge, then you can conclude, then you can walk away saying the process you observed is spontaneous. Okay. So you're either looking at the first scenario or the second scenario, whatever conditions are provided for you in the question. So one of the things that you have to be able to judge as a Chem 1412 student is the process spontaneous? Now, while we're looking at this, do not judge spontaneity with randomness. Those are not the same thing. Spontaneity is arrived at when you judge both randomness and enthalpy change, right? So entropy is just one small part, delta S is just one small part of spontaneity. Delta S doesn't necessarily lead us to spontaneity. When I was a student, I used to confuse this because of just the way my mind works. I like to relate things too early. So when I'm learning something in an effort to survive the pressure of learning something new, I try to grasp at things I already know. It's like, oh, this reminds me of A or it reminds me of B. And sometimes I do that prematurely before I really understand the concept. So I have to kind of hone in, right? So what I'm trying to say is, even though S matches spontaneity, or I guess is the first letter in spontaneity, right? This S here does not stand for spontaneity. It actually helps us to see the randomness or the entropy. So remember, S stands for entropy. I know they didn't make it E, right? E is already taken for something else. So S stands for entropy, not spontaneity. But from the change in the entropy of the universe, we can then judge spontaneity. So hopefully you understand that. If you feel like I haven't given you enough information, please feel free to look at the textbook or the videos by the author. Okay, so we're back to this, right? The total entropy change, where the entropy here has a symbol of delta S, of the universe has to be positive. And they tell you right here. First of all, how do we even figure out delta S? Well, ideally, we want for the equation we're looking at, we want it to give us the delta S of the universe, right? But what if you're not given this directly? If you're not given delta S of the universe directly, the plan B will be to look and see, were you given the change in S of the system and the change in S of the surrounding? If you were given these two numbers, you can add them, right, to get the change in S of the universe. So look at the entropy of the system and the universe. We don't need the value of the S of the universe, or the change in S of the universe. We need the sign. All we need is the sign. Okay. As long as it's positive, if this number here is positive, the reaction is spontaneous. So we're told here, for a reversible process, delta S of the universe is zero. Okay, zero positive, no. Zero is neither negative nor positive. So for a reversible process, we're reviewing this again and we're being told this is not going to be spontaneous. Not spontaneous because it has not met the prerequisite, the requirement, right? What about for an irreversible, a one-way reaction? For an irreversible process, aka spontaneous, that process will be spontaneous. Why? Delta S of the universe is greater than zero. It is positive, right? This means positive. Okay, so now we're kind of moving on. Once we have defined that, we're moving on. If the entropy of the system decreases, okay, as I am trying to read this, let me actually add this to a brand new page, because I feel like in this chapter here, decoding all the stuff that we're reading is so important. Let me see, did they add that here? Oh, I forgot I did this before. I did this before. So listen, a week has passed and I haven't reviewed these notes. I've been doing other things in the weekend. You know how that goes. Okay, so we are going to be working on this here. If the entropy of the system decreases, right? So delta S of the system decreases. Decreases just means this is negative. If it's decreasing, it's becoming more ordered, right? If it's becoming more ordered, it's going from, let's say, a gas to a liquid, or a liquid to a solid, right? Delta S of the system decreases, i.e., becomes more ordered. Okay, so the way I was able to understand these words when I was learning them years ago was to kind of relate it to people, right? I feel like mentally I can comprehend people, not chemicals so much, right? So when I get stuck, in dealing with chemicals, I try to tie it to people. Now, I don't tell the people I'm thinking about, just random people that I make up in my head. When the system is becoming more ordered, in other words, it's going from being random to more ordered, delta S decreases and delta S is negative. So the way I view this relating to people is saying that the system or entropy in general does not prefer a very organized person. I am not super organized. I'm way too random to be super organized, right? So my argument is usually even nature prefers randomness, even nature prefers a little chaos, right? So if someone has a tendency of being too ordered, too organized, too OCD, everything has to be a certain way, that the delta S for them is usually, if there's a system, is usually negative because you're going from a more random, so you're going from more random to less random, right? And so if you were judging their behavior, matching it to a physical transformation, more random will be like gas molecule behavior. Gas molecules are very energetic, they're very random, they move around in straight lines, but they're constantly in motion, high energy, right? And then less random is ordered, more grounded, like liquid state, or even more ordered would be like solid state, right? Organized, stable, not moving around, where you leave it is where you will find it hours later, right? Gas molecules constantly in motion. So more random, less random. And I use that to relate to people and then back to chemistry. So it's just a detour, but I'm ultimately trying to learn the chemistry. Okay. Anyway, so yeah, especially with conceptual stuff. So delta S system is, let me pick one. So I'm going to say freezing. Okay, so my illustration here, does the S system decreases is negative. That means I'm dealing with freezing. In freezing transformation, you have a liquid freezing to form a solid. A liquid has a higher entropy than a solid, so that is consistent, right? The entropy is decreasing. Okay, what else? So I'm right here. Then the entropy of the surrounding must increase by a larger amount. Okay, so let's see how the entropy of the surrounding is changing. When we go from, let me examine the reverse. So examining uh, enthalpy change in the reverse process. So if you are like me, right, you're like, wait a minute. If we're really focusing on a system where a liquid is becoming a gas, why are we examining the reverse process? I think that we are, as humans, we naturally relate to a solid melting more than a liquid freezing. So I'm going to look at that and just flip this sign when I'm done. And then we'll be back here. Okay. So we're examining the enthalpy change in the reverse process. So we're trying to see, remember enthalpy change is delta S. I'm sorry, delta, I'm saying S and I'm writing H. Oh my goodness. Delta H, right? We're trying to see the heat transformation or the heat movement in this transformation. So in the reverse transformation, a solid goes to a liquid by gaining heat. When it's gaining heat, what do we say about the delta H? Delta H is positive, right? Because heat is gained. So if going from a solid to a liquid requires gaining of heat, then going from a liquid to a liquid to a solid will require a loss of heat, right? That's what I'm saying. It's hard when I ask questions like this on campus. It's hard for my students to give me the answer from this without going, uh, uh, then there's a long pause. But I feel like if I start with something that we can relate to quicker, that is solid melting, in order to melt a solid. So this example I'm providing here is under the context of melting. If you have a piece of ice and you want to melt it, you have to add heat to melt a piece of ice, right? Adding heat means the system, which is the ice, gains heat, that means delta H is positive. But if you want to freeze a liquid to form a solid, water to ice, this is freezing. Freezing actually requires the system to lose heat because it's the opposite direction, right? Now that we're doing that, now I can go back and use this second situation here that applies to our transformation, right? That we're looking at and say, we really don't care about this in this context. I was just trying to mentally get us to this point where we can say the enthalpy change for the transformation we're looking at is negative. Okay. So now that I have made that conclusion, I can now fill in the gaps and say, when a liquid freezes to form a solid, comma, heat enthalpy is lost by I just call it the system versus saying the liquid. The system, aka the liquid. In the process of forming the solid, the liquid ends up losing heat. Okay? Now, where does that heat go though? We get that the system is losing heat. Where does the heat go? Based on what we've seen here, the heat lost by the liquid, also called the system in general, is gained by the surrounding. Okay? So in chemistry, there's a lot of that give and take relationship, right? Where one part of what we are observing is given, the other part is taken. When we were looking at redox reactions in 1411, right? One was giving up electrons, the other part was taking. That kind of, I call it the yin and yang relationship, where there's a give and take, like the two halves of a whole, right? Here we're seeing two halves of a whole. The part of the system that gives off energy, and then the other part, which is the surrounding, that takes up the energy. That anytime a system loses energy, a surrounding takes up that energy. If the system is losing energy, there has to be a surrounding to take up energy. Energy is never just lost into nothingness. Okay? Something has to be ready and available to take up that energy. Okay, so back to what they were saying. If the entropy of the system decreases, we said that, right? Then the entropy of the surrounding must increase in a larger amount. Okay, so I'm not done. So we realize what happened, right? In the process of forming either the solid or whatever, we're dealing with freezing, right? In the process of forming solid, the system lost heat to the surrounding, and then the surrounding finally uses the newly gained heat to increase its entropy. I need to start the statement with a big T. The lower the starting point, the starting temperature. The point I'm talking about here is the temperature. The lower the starting temperature of the surrounding, I'm running out of space. The greater the entropy change. Okay. I know I wrote this whole paragraph, and you're probably thinking, oh my goodness, we don't do words in chemistry, because there's a lot of things happening here, right? And I told you I like to relate things. somebody in my one of my students was explaining to me how things happen in football, American football, and somebody takes the ball and throws it to somebody else, and then somebody throws it to somebody else, and I'm like, whoa, that's like Gen Chem 2, right? 1412, where in order for one action to take place, you have a lot of players involved, and this person does stuff, and then the other person responds and stuff. Okay, so I probably should stay away from football analogies because I'm not even good at the game, getting what's going on. But there's a lot of stuff happening here. The liquid is becoming the solid, right? The delta S of the system is going to decrease. Delta S of the surrounding is going to increase. So the system is increasing because S, the solid, is less random. The surrounding is increasing because absorbed energy from system. Okay. So the surrounding is like, you're lost. So this is me imagining the surrounding talking to the system saying, it's your loss. You gave up your energy to become less random. In the process, I took your energy, absorbed it, and then used that to make myself more random. Okay, so the surrounding took the energy that the system was giving out, absorbed the energy, and became more random. So there's no accusation here. It's just that if the system is not going to handle its energy and it's going to just give it away to the surrounding is going to take it. It's like, I will absorb your energy and become more random. And so in the transformation, once everything is said and done, the system is less random, but the surrounding is more random. Okay, so hopefully you're seeing what happened here. That's the bottom line. Okay, what was it saying again? So when this happens and the surrounding is not just more random, but very, very random by larger amounts, then we're told when a system is negative, like we just saw, the surrounding must be positive and big for a spontaneous process. So, I realize what they're saying. They're saying that it is possible for a liquid to become a solid. Isn't that what we call freezing? Right? So I would say in Texas, or anywhere else, but since we're in Texas, comma, liquid water will freeze to form solid water, aka ice. And of course, we call this snow, right? So instead of calling it just ice, I'll call it snow. When the surrounding temperature is low. As I'm looking at the time, I'm thinking now we're going to have a part 2 and part 3, maybe even a part 4 for this lecture. But it's important for me to explain this part so you understand this conceptual part, because they go over it over and over again in the chapter. If you get it here, when we get to the other parts, you can skip over it, okay? So in Texas or anywhere in the US, liquid water will freeze to form solid water when the surrounding temperature is low. When the surrounding temperature is low, then remember liquid is forming solid. The following conditions apply. The delta S of the universe, remember that's the one that we're using to judge. Let's see what's going on. Delta S of the system, according to what we learned up here, is negative, right? Delta S of the surrounding. So the surrounding is like, listen, system, you lost your energy. You gave up your energy to me. I took your energy and I became random, very random, so much more random that I am more random than you were. Okay. So if the temperature is low, temperature of surrounding is low, then we're told here the magnitude by which the surroundings entropy will increase will be really high. So to kind of make this make more sense, I'm going to assign numbers to it. Let's say the amount of energy the change in entropy of the system, let's say is negative 10. Okay. The system went from being, let's see, it's final minus initial. It went from being 20 to 10, right? So it's final minus initial negative 10, like that. Then the surrounding, that is at a much lower starting point in its temperature, right? It's cold, so it's about 5 degrees in Texas, like what happened this year, low temperature. The surrounding takes the energy lost by the system in the process, and it increases. It increases to like 25 as far as its entropy. So remember, now we're even though the energy was the one that was absorbed by the surrounding uses that energy to increase its entropy. And all we're doing here is comparing the entropies. So when you add these two, we get a net positive of 15, correct? So that means that even though the entropy of the system became lower, the surrounding increased so much to kind of cover the system to where the universe has a positive entropy. So this will happen, this occurs spontaneously. Okay? So in other words, I said all this, did all this math to conclude that when the temperature in the surrounding drops, it's going to freeze. That would have been the simplest way for me to say this. As it got so cold this year, it got to 36 and we're like, whoa. It got to 37, 36, then it dropped to 20, then we saw 9. I never stepped out because I was thinking about time. I'm just kidding. I'm just kidding. I did think about it a little bit. But I was just thinking, freezing pipes. It's so cold out there. We're in the people who were walking the streets. Okay, they're walking when the entropy of the universe is positive, and there was ice everywhere, spontaneously. Okay, so now we kind of move on. Finally, we're moving on, looking at changes in entropy. So now we're looking at entropy versus back at the universe. We're told to figure out the change in entropy. You want to know the final entropy and then the initial entropy. So please notice for these state functions, which we talked about in 1411, state functions, these are special thermodynamic measurements whose value depends on the final and the initial value. Okay, whose magnitude. So state functions, the change in the magnitude depends on the final and the initial value. So what I mean by that is, look at the example of state functions: delta H, delta temperature, delta volume, delta S. We're going to be looking at delta G at some point. First of all, look at what they have in common. They all have the sign delta. Delta signifies change. When you're trying to figure out how these values are changing, the biggest thing you need to have, if you were in the lab recording values, you want to record all the individual changes, right, at every point. But you have to make sure you have the initial change and then the final change, because if worst comes to worst, having the initial and the final amount will allow you to calculate the overall change. Okay, so to get the overall change in any of these state functions, all you need is the final and the initial value. So for enthalpy, final minus enthalpy initial. Temperature final minus temperature initial. In 1411, we did that, right? Volume, usually we look at the volume final minus volume initial. Entropy, we're seeing that right now in context. The final entropy minus the initial entropy. And then when we get to Gibbs energy down the road, we'll do the same thing. Gibbs energy final minus Gibbs energy initial. It's just that we encounter these at different points of chemistry. We don't always look at it holistically, but you want to know what types of measurements in this section or in this chapter are state functions having the following characteristics. And then the other thing you notice, delta, and then the actual measurement is written in capital letters. Okay. Okay. So the entropy change is favorable when it results in a more random system. This is what I was trying to say. Nature prefers a more random system. Nature prefers it when delta S is positive, when you go to more ordered, like liquid, to gas. This happens randomly. Not to say the reverse can't happen. The reverse can happen if you change the environment's temperature, right? Changes that increase the entropy are as follows. So we're trying to look at what kind of things make delta S positive. Okay. If you want to make the delta S, now what it's talking about here is delta S of the system. If you're trying to make the system to become more random, what can you do? If you have a chemical reaction whose products are in more random state, for example, a solid which is more ordered than a liquid, but the solid is becoming a liquid. So if you have a solid converting to a liquid, you know the solid is less random, the liquid is more random. So delta S here is positive, right? Liquid is more ordered than a gas. So then that means that if you have a liquid becoming a gas, like I showed up here, the transformation is positive, has a positive entropy. Why? We're going from more organized, more proper, more feng shui, I don't know, into more random, more fun, right? Increase entropy. Hey, I am not trying to be biased. I'm just saying that this is favorable, okay? It's preferred by the universe. Reactions that have a larger number of product molecules than reactant molecules tend to also have an entropy change that is positive, okay? But with this one here, say for example, let me give you an example of this. If you have sodium chloride, a compound breaking apart to produce sodium ion, and chloride ion, you're making two species from one species, one chemical breaking apart into two chemicals because you have more chemicals in the product. That is more random and that's preferred. If you have a scenario where the temperature of the system increases, so system increase, that is considered more random, higher entropy. So therefore, the preferred. So why is the temperature the randomness? Because gain temperature. It's kind of like getting a caffeine shot, right? They have more around a lot, more random, more change. Okay. And then solids dissociating into ions. I gave the example here upon dissolving. So when you have a solid in water and it forms ions, that's considered more random. So I would say when you're making notes, when you're writing your own notes and you get to this part, in your notebook, you the recording and then write. These are criteria. Let's say criteria. I'm using that word again for a greater entropy. So this criteria here will result in a greater change in entropy. The S would be positive, okay, if the following criteria is met. And then you go through, okay, number one, what do we say? Solid to liquid. Number two, liquid to gas. So you're making notes, right, as you're writing this. Number three, increase product molecules. So here you can give yourself an example. Number four, increase temperature. Number five, dissociating solid. Okay, so you're writing this in your notes. Okay, just like I wrote right here. Then they kind of explain a little bit more here. The entropy change, right? So just reading the graph, as the temperature increases, so does the entropy. For that reason, solids will have less and they'll also have a lower, this is lower entropy. Gases will have, they tend to exist at a high, and they will also have the highest entropy. So I'm those graphs, okay? And they go into the details here. Feel free to read that. Okay, finally, we're working question number one. Predict the sign of entropy change. Now remember, this is not asking you anything about randomness. This is asking you about entropy change. So when you get to this chapter, don't skim over the words. The words are very important. Words matter in chemistry, right? Because when people tell me, well, I don't understand what the questions were in the exam, what they were asking, that means when you were studying, you somewhere were subconsciously, hold on a second, I can get the words right. You subconsciously decided the words weren't important, just the math was. But the words are important, especially in this chapter where most of this stuff is just conceptual, right? The entropy stands for S, and of course, change is delta, right? So we're dealing with delta S here. Let me write it properly. So we want to predict the sign for each process. Oh, that's from gas to liquid, from more random, so greater entropy to less entropy, right? So I'll say here delta S, the transformation, is going to be negative. It's going from more disorganized to more organized, from more random to less random. So delta S should be negative. Solid carbon dioxide sublimes. So a solid is subliming as it goes straight to gas. If it's going to a liquid, it's melting, right? So straight to gas. This is right here in randomness, less entropy to greater entropy, right? So this is going to be delta S is positive. And then here, let's see, we have two gases in the reactant forming three gases, right? So total of two molecules to 2 plus 1, 3 molecules. Number of molecules are increasing. And we said right here, somewhere here, if you have increasing part of molecules, delta S is positive. So you can see right here, delta S is positive. Okay? Hopefully you can see how this applies. Once again, the questions are a lot easier if you don't skim over the words. Spend the time to learn the words, the terminology. Okay. Yeah, delta S is positive, positive, negative. And they give the explanation there, right? I'm not doing the full practice. Feel free to do that part. Okay. Oh, here's where they get to all the details that I already explained. The second law demands. So this is a heat transfer, right? I kind of already talked about that. Heat transfer was delta H and the changes in entropy of the surrounding, delta S. So what they're saying here is what I explained earlier, that we're now just focusing on the surrounding. Okay? What happens to the surrounding? If the surrounding gains delta H from system, because it's delta H just discarded, well, the system just discarded its heat, delta S of surrounding increases, right? That's the bottom line we learned before. So totally the second law demands that the entropy of the universe increase for a spontaneous process, okay? However, processes like condensing of water, vapor, are spontaneous. That means a gas going to a liquid is spontaneous. This has a greater entropy, this has a lower entropy, so delta S of the system is negative. Okay, even though the water vapor is more random than the liquid, right? They're saying the water vapor has a higher entropy than the liquid. Well, why is this spontaneous? Even though delta S of the system is negative, I already explained that. If a process is more spontaneous, if a process is spontaneous, not more spontaneous, if a process is spontaneous, yet the entropy change of the process is unfavorable, meaning negative, there must have been a large increase in the entropy of the surrounding. I already explained that. The surrounding increases in entropy after it gains the heat from the system. The system gives off its heat. The surrounding is like, I'll take your heat. It takes its heat, uses that heat to produce a greater increase in the entropy. And then when you add the true entropy changes, the universe ends up with a net positive. Okay? The entropy increase must come from the heat released by the system. You see how they just kind of put that in there? Yeah, we already discussed this. So there it is again. Hopefully now it's a review. The process must be exothermic. Okay? So now that we explained that, this kind of reminds me of spring cleaning. So it would be, it's just my mind just went to spring cleaning. It would be like you discarding something because you don't need it anymore for whatever reason, and then somebody taking it and then upstaging it, like upstaging you, I guess, taking the thing that you threw away, and then they're doing with it more than you ever did with it. right? So the system loses its heat. But when it loses its heat, the surrounding is like, I will take your heat, and uses that heat to produce a much larger entropy. Man. Okay, anyway. So, yeah. So once we've seen all that, that explains all this, right? So when a system processes exothermic, when a system's process is exothermic, it adds heat to the surrounding, increasing the entropy of the surrounding ultimately. When a system's process is endothermic, it takes heat from the surrounding, decreasing the entropy of the surrounding. The amount of entropy of the surrounding changes depends on the original temperature. I already mentioned this before. The higher the original temperature, the less effect adding or removing heat has. That's why if ice is ever going to form, the original temperature of the surrounding has to be very, very cold. That means that ice will only form if the environment gets very cold. Because when the environment gets very cold, then adding any heat to the environment causes a great increase in the entropy of the surrounding. Okay? So now we're trying to see exactly how does the surrounding take up that heat to cause the surroundings entropy to increase, right? So now we've seen what happens. Now we're trying to see how it happens. Okay, quantifying the entropy changes in the surrounding. The entropy change in the surrounding is proportional to the amount of heat gained or lost, right? That just means that if the surrounding gains a lot of heat, it increases in a lot of entropy, right? Okay, so we're told here the heat, so this Q positive is just saying heat gained. So heat gained by surrounding equal to heat loss by system. Okay, the symbol here negative means loss. It's like, what is it called? uh Finders keepers kind of situation, right? Yeah, I'm trying to relate this to life outside of chemistry. Like the system lost the heat and the surrounding found it, right? Because they have that equal exchange. Whatever the system discards or gets rid of or loses, the surrounding takes, right? So that's what this equation is saying. Whatever the system loses, the surrounding takes. The entropy change in the surrounding is also inversely proportional to the temperature. Now, the temperature here they're referring to is the temperature of the surrounding. We said before, so I like to add here of surrounding. So if the surrounding has a very, very low temperature, mathematically, if this bottom line, bottom number, not line, but if my goodness, if this bottom section is very low, then this is very high. So we saw that freezing will happen when this temperature of the environment or the surrounding is low, and then the system gives up. So two things have to happen, right? Two things have to. I don't know why I'm smiling. It's like I kind of feel like I'm on the side of the surrounding. I just like it when it snows in Texas, even though I know it's dangerous and stuff. But it's because it's not very common, not like Kansas. Kansas was like it snowed all the time. But for snow to happen, then we want the surrounding to have a large positive value, right? So positive and large value. Okay, so this symbol here means system lost heat, which the surrounding took, right? And then surroundings temperature is low. So two conditions required. When the system loses the heat, the surrounding takes it. The surrounding temperature is low. This will produce a large value of delta S. Okay. Okay. So from here, though, mathematically, you want to then understand the equation. To figure out how the surroundings entropy is influenced by the changes in the system, you want to have this equation here. So it says the change in the entropy of the surrounding is equal to the negative change in heat of the system over the temperature. Okay, the temperature here usually refers to the temperature of the surrounding, just the temperature in general. So let's go ahead and work on this process here. calculate the entropy changes in the surroundings. Okay, we're given this reaction here. In this reaction, let me see if I can add a page on the bottom and we'll see how this works out. Oh no, consider the following. No, I'll just say this one here. I want to start with the first part and then we'll go from there. Copy. Okay, let's start with this and I'll deal with the other part. Okay, so in this part here it says calculate the entropy change in the surroundings associated with the reaction occurring at 25 degrees Celsius. So it looks like, well, the environment, right, is 25 degrees Celsius. So we have a temperature that's 25 degrees Celsius. Oh, I forgot to mention right here. They didn't say it. The temperature here has to be in Kelvin. I forgot to mention, and it wasn't mentioned, so that's not, yeah. The temperature has to be in Kelvin. The temperature is 25 degrees Celsius. You want to convert this to Kelvin at 273.15, and that gives you 298, right? 0.15 Kelvin. So we got the temperature of the around, right? That will be the surrounding temperature. Okay, so delta S, I need to write the S bigger, hold on. Delta S of the surrounding is equal to negative delta H of the system over the temperature. Okay, the temperature has to be in Kelvin. I've already done this part. So, by the way, while we're here, please note the system is the chemical reaction. So you want to note this because this is an important note for you to have. The system is the same thing as the reaction. Okay, so I'm going to rewrite delta S of the surrounding as equal to negative. What's the heat of the system? Negative 2044 kilojoules over 298.15 Kelvin. So let me work this out, and I end up with negative 2044 divided by 298.15. Oh, come on. I put the wrong negative. Oh, no, it's not that clear. Oh, I cleared the whole thing. Negative, oh, okay. 2044 divided by 298.15. I end up with 6.6. Oh, no, 6.856. Why can't I? It's kind of dark in here. 6.6, 6.856 kilojoules per Kelvin. So if you want to write it, usually delta S is represented in joules per Kelvin. So I'm going to convert it right here. So times 1,000. This is usually represented as 6.856 joules per Kelvin. Okay, delta S surrounding. So that's my first one. Yeah, they wrote it in scientific notation, but you get the idea, right? That's my first part. Okay, this part is done. Determine the sign of entropy change of the system. So let me go ahead and copy this part. Okay, I'm going to add a page here because I'm going to work this out linearly. Okay. Okay, determine the sign of the entropy change of the system. So the system is the reaction, right? So what I'm going to do here is, wait, okay. What I'm going to do here is copy this, the reaction over, just the reaction part. And they want the sign. Okay, come on. This computer is, the iPad is responding a little slower than I like. Anyway, here. Okay, so what I'm going to do right now is count my gas molecules, right? So I have 1 from here, 5 from here. So I have 6 molecules, 3 from here, 4 from there. They're all gases. Seven molecules. Okay, I'm making more product molecules. So from here, I can say delta S is positive, Y greater product molecules. Okay, so remember that list I made way back here? That's the list that you use to judge a reaction by. Criteria for greater entropy in chemical transformation. Because it can be a chemical reaction or just, you know, whatever, a physical reaction. These two are physical, right? But whatever we're focusing on, I usually say the chemicals are the ones that you apply these rules to, okay? To figure out that the S is positive or negative. So back to what I was doing. Where was I in that question? It appeared like a simple question, but you want to be able to apply all of this. Okay, greater product molecules, finally. Okay, so I did number B. The number C, it says, or you should say number C, letter C. Letter C, let me copy this. Letter C says, letter C sounds weird. I like number C, but I know C is not a number, it's a letter. Okay, I know. Okay. Determine the sign of the entropy change for the universe. Is the reaction spontaneous or not? Okay. Delta S of the universe, we said, according to second law of thermodynamics, is delta S of the system plus delta S of the surrounding. Okay. What all we need is a sign, right? So we're gonna just use the sign. So what is the sign on the system? We just did the work. Positive. What was the sign on the surrounding wall? Because there was nothing here, positive. If two positive numbers are added, what does it produce? This is adding, sorry. It's like plus, plus, plus. If you add a positive number to a positive number, what do you get? Positive, correct? So this is positive, the other one is positive. So delta S should be positive. Therefore, delta S of the universe is positive. And transformation should be spontaneous, right? So it's kind of like writing an essay, but not really. Therefore, okay, let's see how they concluded. Delta S is surrounding, is positive. Delta S of the system is positive. The change in entropy of the universe is the sum of the entropy changes of the system and the surrounding. If the entropy changes of the system and the surrounding are both the same sign, which in this case is positive, the entropy change of the universe has to be that same sign. Just say positive, positive, right? So this is positive and that's positive, and this is positive. I'm like, okay, okay. I'm not going to judge what they're saying, and therefore the reaction is spontaneous. I'm going to judge how they're saying it, okay? I'm sorry. Sometimes I'm just stirring up drama just because. Okay, you can work on the full practice one if you need an extra one, but there's no answer here, right? But I'm so happy we're making progress. Look, the slides. Temperature dependence. We've kind of talked about this before, but they're going over it again. So I'm just gonna read through this and not really overly explain it. So we know delta S surrounding depends on temperature, right? Even that equation, delta S of surrounding. Y'all know when I was in school, I really struggled with this section. It just so foreign to me. Then I started teaching and I'm like, what? This is what they were saying this whole time? I have an anxiety of learning. When something is new, I'm like, I don't know what to expect. So then I just kind of judge it's gonna be really, really difficult. And to be honest with y'all, not to be I say okay, to just tell you my experience, we were learning this in junior level, well, sophomore level chemistry, then again in junior level chemistry, and there was calculus and stuff around it. So versus giving me peace about it, I don't know. I'm just the kind of person who overthinks things. So I was like, oh, this must be really bad. Now I'm like, oh, this is all they were saying over and over again. So the entropy of the surrounding, right? We saw in the formula, essentially entropy change of the surrounding can be figured out from the system. Just take the negative delta H of the system divided by T, right? Since to get the surrounding, you need both the change in heat or the change in enthalpy and the temperature, then the surrounding entropy depends on temperature. So temperature dependence of the delta S of the surrounding is not a new concept. We have seen that before. We're just saying that this number here depends on temperature. Okay? So when the heat is added to the surrounding that is cool, right? If heat from the system goes to the surrounding that is cool, it has more of an effect on the entropy than it would have if the surroundings were hot. Okay? So that's talking about the temperature of the surrounding. If the temperature of the surrounding is high, if this temperature is high, then this number, change in surrounding, is going to be low. But if temperature, let me use a different color. If the bottom temperature is low, then the surrounding delta S will be high. This is just a mathematical concept, but they're saying it again as far as the chemistry concept is concerned. So if the surrounding has a lower temperature, this means T is low, right? Surrounding that's cool, then there's a greater effect on the entropy change. There will be a greater effect on the change in entropy. If the surrounding is hot, and hot, that means temperature is high. That means the change in entropy will not be as high. Okay? Water freezes spontaneously below 0 degrees Celsius because the heat released on freezing increases the entropy of the surrounding enough to make delta S positive. So when the temperature is 0 degrees Celsius, then the bottom number in Kelvin is going to be what? Is 0 plus 273.15. 273.15, if you're trying to freeze for Kelvin, is low enough so that whatever the delta H is for, let's see, you're going from liquid to solid. When liquid water is trying to become a solid water, as in ice, the delta H released in the system is very high so that when you divide these two, we get a very large positive delta S of the surrounding. That's what's being said here. Versus how easy is it to freeze water when the surrounding is 35 degrees Celsius? When the surrounding is 35 degrees Celsius, now you're taking 273 and adding 35 degrees Celsius. Freezing may happen because the delta H system doesn't change, right? Freezing may happen, but what about, let me choose one that's close to impossible. Let's say you have 40 degrees Celsius, right? So now you're adding 40 degrees Celsius to 273, and then the number down here is very big. It makes this much smaller, and so freezing doesn't usually happen at 40 degrees Celsius unless the pressure changes, because we learned before, right? Freezing, change of state is not just about the temperature, it's about the temperature and the pressure combo, right? So above 0 degrees Celsius, the increase in the entropy of the surrounding is usually insufficient. It's not enough to make delta S of the universe positive or delta S of the surrounding positive. Okay. So they show that to you. When you have low temperature in surrounding, this picture is helpful, but for me, the math is more helpful. Delta S of the surrounding. Your goal is to make this large and positive. So once again, the negative delta H of the system, which this is a fixed number, divided by temperature. Temperature can change. Temperature can be low or high. Delta H of the system is constant for every reaction written, right? So this part here is somewhat constant. Let's assume it's constant because you're trying to freeze the same chemical, liquid, solid. The temperature can be low and high, or low or high. When the temperature is low, water freezes because this number is low, making this number high. And they're showing it to you here. right? The surrounding is so high compared to the system, so the universe, sorry, is positive. When the temperature of the surrounding is high, maybe like 50 degrees Celsius, even though the entropy of the surrounding increases, it doesn't increase enough to overcome the issues with the entropy decreasing in the system. So the entropy of the universe is negative. So freezing doesn't usually happen, doesn't happen at 50 degrees Celsius. Okay. So once again here, you want freezing to happen, drop it to 0 degrees Celsius. So I won't go over that again. Finally, we're moving on to Gibbs free energy. Okay. A process will be spontaneous when delta G is negative. Okay, since we just said that, just flat out, out of nowhere, bam, a process is spontaneous when delta G is negative. I want to go ahead and add a page here. Okay. Every time we add a new criteria, I want to recap. So recap, I know I rarely recap. The recap of the recap. Number one, criteria, criteria, conditions. Okay, because I've already used that word. Conditions for re. It's not necessarily a reaction, just transformation for a process to be spontaneous. Okay, for a process to be spontaneous, the following conditions have to be met. Okay, number one, delta H, delta S combo. Delta H is preferred to be negative, delta S is preferred to be positive. When these two are what they are, judged together, comma, a process is spontaneous. So I'm kind of paraphrasing it, right? You have to judge these two together. Number two, delta S of the universe is positive. Okay, so regardless of what you have, delta S of the universe, we know you get this from delta S of the system, and the system is also the reaction plus delta S of the surrounding. And as long as both of these give you a positive delta S of the universe, delta S of the universe is positive, or has to be positive, I should say here, has to be positive for a process to be spontaneous. Okay, so if it's positive, it's spontaneous. Okay, number three, as we move on, delta G, which is now called Gibbs free energy. We haven't defined this yet. We're still talking about the criteria, but we'll talk about it down the road. Gibbs free energy has to be negative, right? Delta G, Gibbs free energy, has to be negative for a reaction to be spontaneous. Okay, now we have three different criteria, three different conditions. It's either the first one or the second one or the third one. If you have more than one of these conditions, criteria provided for you in the question, it's up to you to pick what you want. Okay, I will tell you my preference. My preference is delta G, even though we're learning it as a third one. Why? Because delta G to me is the least complex. Yeah, you will see different formulas on how to find delta G, but I feel like of all the things, it's kind of the least complex, right? To get delta S, the universe, they usually give you system and surrounding. You have to add that. With this one here, you have to have both numbers, or else you're not really getting the full picture, right? You can't make the conclusion with only delta H with delta S. You have to look at them together, judge them together. So I feel like, and you will see how the author also chooses to approach this. Okay. I know. You probably feel like this is a lot because it's that time of the semester, right? But the reality is you're trying to learn how to reason through bulk amount of information, and you're trying to learn how to sort through things, which is the preferred method, usually the simpler one, right? As you're studying, look at what the author chooses, because with you guys, I mean, if you are reading different books, you tend to see how different authors have different approach to the same problem. With you guys, not, I guess, with this generation, not necessarily reading two or three books at one time. My generation, I know this really ages me. Back in the days, right, when Google wasn't what it was right now, where you can just go and Google something and stuff like that. It was very normal to have a question about Gibbs energy and really try to see the approach on how to deal with that. You go to the library and you get like three books. I mean, two books, three books, yes. You got three books, and then you got to the page where Gibbs energy was defined, and you were trying. So you read three books, and of the three books, one of the authors will say what you will say the definition, they will write the concepts out in a way that made sense to you, and then you go with that author, and then you kind of read that chapter at least, okay, because the way the author presented the material kind of went with the way you think. Energy, so it's that's weird. I don't know why it does this to where I hear my voice like something is happening, like kind of a weird audio feedback. Anyway, so what was I saying again? Oh yeah, you get to pick which one to use, but it's all also based on what is given to you in the question, right? So when you're approaching a question and they're asking you, is this reaction spontaneous? You're like, okay, I am armed and I am ready to answer this question based on the following three criteria, right? Let me know. What is the question? I have three criteria. Okay, so back here. Excuse my excitement. I told you my delta S is high, it's positive. It, for me, it's exciting because this is one of those chapters that was a challenge when I was in school. I was like, what is this? And who did this? And why would people even major in this area of chemistry, physical chemists? Why would you even major in this? But then later on, I was like, oh, it's not that bad. Okay, okay. So I get excited when I teach about it because I feel like it's demystified to me and it's less scary than what it was before, right? So a process will be spontaneous when delta G is negative, stated, and we've listed it, right? Delta G will be negative under the following conditions. When delta H is negative, delta S is positive. Wait, haven't we stated this? Isn't this like a deja vu? Isn't this like our first reactions right here? Delta H is negative, delta S is positive. Do you see what I'm saying? How they're writing? Mm-hmm. If you have a situation where the reaction is exothermic and more random, at that point you have a choice. You can use these two to decide the reaction is spontaneous. Okay. Now, the issue here is we're now kind of stepping away from this first scenario and we're looking at other delta H, delta S combinations where things are not that simple. Scenario two, you have delta H being negative and large, delta S being negative but small. Wait, both delta H and delta S are negative? And somehow delta H is negative and large. Delta S is negative but small. So we're being told here, this second condition here, where you are looking at both these numbers, delta H and delta S, and still concluding that when you have a delta H that's negative and large, delta S is negative and small, that will produce a spontaneous reaction. Okay, I'm pausing for effect. Okay, as a student, I know that the kind of learner I am. When I'm invested in something, I don't even have to care about it that much, but invested because of a grade, I'm like, wait, hold up a second. I was with you on the first point. The second point, I feel like I'm memorizing. I've moved away from understanding to memorizing. How am I supposed to just know? Delta H negative is large, delta S negative is small, and somehow these two combinations produce a delta G that's negative. Okay, we'll come back and answer that. Condition three, delta S is positive but small, delta S is positive but large. Well, here's the thing. You can memorize this and it works. If you are great at memorizing, you can memorize this. If you are not and you need to understand this scenario, then I'm going to show you how I was able to survive this, right? Because at a certain point in undergrad, when I got into junior level, of course, I was taking a bunch of chemistry classes, physics classes at the same time. I didn't have a lot of time to invest in memorizing, right? So how am I, a young lady, supposed to survive school when memorizing isn't my strongest suit, right? It's not the best way I learn. And I'm reading something like this, and it's junior level, so you're doing research, you're doing all this stuff. Anyway, I'll show you guys how I did it. Delta G will be positive under the following conditions. Okay, delta G is negative when we have a spontaneous condition. Delta G is positive when we're not spontaneous. So you see over here, they chose the opposite conditions. Delta H is negative and small versus large, and S is negative and large. Once again, so at this point, I'm just kind of going through the motions, right? Delta H is positive, delta S is positive and small, delta H is positive, delta S is negative, and then we're kind of going through all this. And then we're told finally when delta G is 0, the reaction is at equilibrium. So this part here is important. Not to say the others aren't, but we will go through and talk about this, okay? So delta G, when it's less than 1, or negative, I should say less than 0, not less than 1, because it's negative. You can't be equal to 0. Less than 0, this is spontaneous. Delta G, greater than 0, non-spontaneous. Delta G equal to 0 at equilibrium. So equilibrium seems like the halfway point, like the midpoint between spontaneity and non-spontaneous. So when you go from spontaneous, you get to the middle equilibrium, then you skip over non-spontaneous, something like that. That's how I view it in my head. Okay. So now that we've seen this, now let's move on and see. They give us a chemical reaction. Sorry, a chemical equation. This one right here. It can be shown that negative T delta S of the universe is equal to delta H of the system minus T delta S of the system. I'm trying to think about where do they get this from? I'm trying to think back. But for some reason right now I just can't remember how we got here from what we were looking at before. Because it's talking about the universe versus the system. Anyway, working with this here, we then see that this is the relationship between delta G of the system, delta H of the system, delta S of the system. So we will go back to what I appear to have skipped over. I hadn't skipped over this. I just want to explain those in the context of this equation right here. So before we continue, Gibbs free energy is the maximum amount of work energy that can be released to the surrounding by a system for a constant temperature and pressure system. So remember in this chapter of thermodynamics, right? Thermo refers to heat or energy. Dynamics refers to motion or transformation or moves, right? This is a chapter where we are looking at energetics. Energy in chemistry being moved from one place to another. It would be like if you were in business and you're looking at your goods and wares. This is taking me back, being transported from point A to point B in one of them 18 wheelers, right? So the 18 wheelers is a system that's transporting your goods from point A to point B, right? Only here we're thinking about energy or heat being that which is transformed or transferred from one area to another. The one area is usually the system, to another is usually the surrounding. Okay. So apparently there are different kinds of energies. We've seen all of those different kinds of energies, and those different kinds of energies are also referred to as thermodynamic functions. So Gibbs free energy is a unique kind of energy from the other energies we've seen. Remember delta S or S deals with the energy associated with randomness. So if a system is random, very random, its S value is higher. If a system is not as random, its S value is lower. The energy contained within the system is H, right? The energy inside the system or stored inside the system is H, enthalpy, right? So if the energy changes, is lower, we say the system lost energy. If the energy becomes higher, the system gained energy. Now we're looking at a whole different type of energy, and this energy is apparently the energy associated with work. Okay, so not all energies are alike. This Gibbs free energy is essentially the energy that is dedicated to work, available to work. So it's called free energy because the energy is not being used to maintain other systems or to maintain other entities within the system. This energy is the energy that is free or available to do work. So Gibbs free energy, G, is the maximum amount of energy that is available to do work. And it can be released to the surrounding by the system for a constant temperature and pressure system. Gibbs free energy is often also called chemical potential because it's analogous to the storing of energy in a mechanical system. Okay, so let's detour a little bit. If you're into health and yeah, if you're into health and stuff like that, you want to make sure if you're working out and counting your macros. Okay, I know a little bit about that. Once again, not enough to do an analogy, but just a little bit. Okay, you're counting your macros, you're counting your calories, counting something that has to do with food. It's important for you to eat quality food, the kind of food that keeps your energy up. So we know that food essentially is made up of chemicals. And the chemicals store energy in their bonds, right? So chemicals have chemical bonds. And different kinds of food have different kinds of chemical bonds. Therefore, different kinds of food have different types of energy in the bond. And therefore, different kind of food have different kinds of calories, right? So we know about our high calorie foods and our low calorie foods. So when we talk about chemical potential, sometimes the chemical potential is talking about the potential energy stored in those bonds, right? So if remember, potential energy is stored energy versus kinetic energy. So when they refer to Gibbs free energy, it's not the energy that's out there doing stuff. No, it's the energy that can be out there doing stuff. So when we're trying to get Gibbs energy, we're trying to get the energy that we're about to convert into some kind of kinetic energy and do stuff. But until it gets converted, it's being stored. It's like a savings account. It's being stored for a rainy day. But it can be, if needed, it can be cashed out, converted to kinetic energy, and used to accomplish something. Okay? So remember, potential energy is stored energy. It's not being used yet. But if necessary, it can be used, converted to kinetic energy, and used. Okay. So after I've explained that like 2 or 3 or 4 times, Gibbs energy can then tell us by looking at the system, it can tell us if that reaction is spontaneous by the way the Gibbs energy changes. So in a chemical reaction like a system, delta H of the system, the enthalpy, the energy currently in the system, delta S of the system, energy due to randomness, you look at that, look at this, and then these factor into delta G, and you can conclude if the reaction is spontaneous or not. We're told here, because delta S of the universe determines whether this process is spontaneous or not, delta G can also determine its spontaneity. Delta S of the universe is positive when a reaction is spontaneous. So when a reaction is spontaneous, delta G is negative. Okay, they write a little differently over here. So what I'm going to do here is let me take a swig of water here. Okay, let's look at the equation. Delta G equal delta H minus temperature delta S. Okay, I want us to examine this table. This is one of those tables where we don't rush over it. Okay, spend some time to study it. We're trying to look at the effect of H, delta H, enthalpy, delta S, entropy, and temperature, the effect that these have on spontaneity. Okay, remember, we concluded before. Let me see if I can move this lower. Copy. I'll write this down here because I want to write and be able to see this. Paste image. Okay. We said before, for a reaction to be spontaneous, delta G has to be negative. So whatever this number is, minus whatever delta S is in T, we want delta G. Our goal, if we're trying to make a process spontaneous, we want delta G to be negative. Okay? Okay, they're saying when delta H is negative, when delta S is positive, and we have a low temperature, that condition is spontaneous. Okay, so what we're going to do, since we already have the answers, is to prove if the following is true. Okay, so delta G is equal to delta H minus T delta S. Okay, so if delta H is negative, let's say this is negative, and delta S is positive. So it's positive. And T is low. Okay, so here's the issue. When I say low and high, I'm like, I want numbers that kind of are easy to relate to. So what do we want to pick for low? 0 degrees? But we can't pick 0 because it will zero out. This factor has to remain. So what do you want to pick? Maybe 25 degrees Celsius? Okay, let's assume low temperature is room temperature. And then high temperature, I haven't tested this out. Let's see if it works out. 100 degrees Celsius. Okay. So low temperature is room temperature, 25 degrees Celsius. 25 degrees is what? 25. Oh, come on, calculator. 25 times 273.15. 25 ends up being, oh, why am I multiplying this? 25 plus 273.15. My husband walked in here and I got distracted. It doesn't take much for me to be distracted. 298.15 Kelvin. Okay. 25 degrees Celsius equals that. 100 degrees Celsius equals 3. Okay, let me write this to the left. 25 degrees Celsius. Oh, could I use a much easier number? Oh, hold on a second. Let me use 300 Kelvin. 300 Kelvin minus 273.15. Hold on a second. Okay. Yeah. Okay, so my low temperature will be 26.85. Does that work? 26.85 plus. I'm trying to use easy numbers. 26.85 plus 273.15. Does that work? Oh, okay. So my low temperature will not be room temperature, be slightly higher, 26.85. And then when I add this to 273.15, I get 300 Kelvin. Okay. This will make my math easier. Why use complicated math, right? And then let me make my higher temperature then 126.85. When I add 273.15, does that work? Yes. Okay. So 126.85 degrees Celsius. This gives me what? 400 Kelvin. Okay. So I got numbers that are easier to work with. You can sense the excitement in my voice, right? It's the small things, right? Okay. Because we can easily multiply these numbers. They're not very complex. Low temperature 26 degrees, 26 approximately degrees Celsius. High temperature 126 degrees Celsius. Okay, so here we're saying that delta G is essentially negative when delta H is negative and delta S is positive. So it will help if I pick a delta H value. I guess I'll just pick a value. Let me say my delta H is equal to 10,000 joules. And delta S, let's say, is 100 joules per Kelvin. Okay? So I'm just picking, once again, easier number to work with. Let me see if this works out. If H is 10,000, 10,000 joules, right? And then temperature here is 300 Kelvin. I forgot to, oh yeah, I got the units right. And then S is 100 joules per Kelvin. Does this work out right? Let's see. Multiply. This ends up with -3 with 4 zeros. And I have 1 with 4 zeros. I end up with -2 with 4 zeros. Yes, delta G is negative. Okay, so I just picked some numbers. I picked a temperature that tends to be low, like something close to room temperature is low, and then something close to boiling is high. But I wanted everything else to work out easily for me. When delta G is negative, this is spontaneous. We're judging spontaneity based on the magnitude, not the size. Sorry, magnitude is size. Based on the sign, not the magnitude. Okay? So when this is negative and this is positive, the reaction is spontaneous. Why? Our delta G value is less than 0. When the temperature is high, let me try the same numbers, but now with a higher temperature. Let's see how that works out. Okay? This is a smaller temperature, right? So the higher temperature, I don't see this working out any differently. Oh, because yeah. Okay, sorry. Low temperature we saw was spontaneous, right? High. Okay, you can tell I am really flying by the seat of my pants. I haven't worked this out earlier. This is me just trying to work this out. Temperature is high, right? So I'll try the same thing, same numbers. 10,000 joules minus higher temperature is 400 Kelvin. Multiply this by the same number, 100. Oops, come on, joules per Kelvin. Multiply this out, we end up with -4 T, yeah, -40 joules. And then here we have 40,000 joules, and then we have 10,000. Okay, so I end up with delta G of -30. I have one less zero here, right? I just realized that. Yeah, -30,000 joules. Delta G is still negative, therefore it's spontaneous. So what we are seeing that when you have the conditions I stated earlier, where delta G is negative and delta S is positive, those types of reactions are spontaneous regardless of the temperature of the surrounding. If the surrounding has a low temperature, this reaction is spontaneous. Surrounding has a higher temperature, reaction is spontaneous. These reactions are spontaneous at all temperatures. So from here we can conclude, now that I kind of got that to work, when delta H is negative and delta S is positive, reaction is spontaneous at all temperatures. Okay, so I'm just going to finish this table and then wrap up this section. That's it. Then we'll have one more session, or maybe two more. I don't know. Okay, now let's judge the opposite conditions. What if delta H is positive and then S is negative? I'll try to stick with the same numbers, okay? So this time, delta H is positive, delta S is negative. Okay, so delta G will be equal to, oh, I just realized, ah, snap. I just realized something. Ah, oh my goodness. Okay, hold on.